Creativity is contagious. Pass it on. With these words, with these novel and golden words of Albert Einstein, the well-known physicist, let me welcome you all for today's new session of My Teacher, the biggest classroom of UAE. As you know, it's a live classroom. You are very much able to ask your doubts and queries over the phone or SMS, or we can send it through mail as well. Today we will focus the contents of physics of grade 12. So I invite the grade 12 students who are doing physics in the Indian curriculum schools. Please join me for this hour, the coming hour. We will spend some time on your first unit of physics of grade 12. Okay, hope the thing is clear. So you may have your textbook or notebook with you. You can work it out. So let us move on for today's class on electrostatics with the let me first show you two basic simulations which will help you to understand the concepts of electric field and capacitors. You know, in the electrostatics chapter. So let me first of all let me tell you something. Today's session I divide into this plan. First of all, I will show you two presentations or simulations which will help you to understand the two concepts in the first unit. First unit in the sense the first two chapters of your textbook as per the NCERT textbook. Second thing, we will discuss some questions which were asked in the previous board examination papers. So from the first unit. So in any course of time, if you have any doubts or confusions related to what we are discussing now, or if you have any questions in store to ask me, surely you can call me and let us sort out what can be the possible solution. In case if you are late in calling, if you are late in getting back to us, you can surely send your questions over the SMS, or you can send it through the mail, so that we will sort it out in the next week. So Monday is a day for doing physics of grade 12. Of course, on Wednesday, another physics session will be coming to do some contents of grade 10. So be ready for that as well. Another teacher, Deepthi ma'am, is going to join us on Wednesday. Today, let us see what all ways we can explore through electrostatics. And before we begin with, let me tell you one more thing. That is, when we discuss some questions, it's not only that particular question you have to be familiar with. You think of what is the concept based on which you are doing the question, and refer that area and the equations or related contents, and try solving more and more related questions yourself, so that the concepts will be more and more clear. Right. So first I will show you a small simulation by which you can understand the concept of electric field. I invite your attention to the screen. Look at this. See, first thing, just if there is a positive charge here, you see the positive charge kept here. So what will be the direction of the electric field line? So I will show you the electric field. You see the electric field lines can be plotted like this. These are the electric field lines. It's away. Instead, if I am taking this positive charge and keeping it back to the bag, keeping a negative charge, you see how the direction of the electric field lines, they all are towards. So electric field lines are always towards the negative charge, whereas it is away from positive charge. Right. And next thing what we have to see is, I will show you the direction of electric field as well. You see, you can make out the value of the magnitude of the electric field is represented by the length of this. So the direction of the electric field is towards this. You can make out. See, as I move away from the negative charge, the magnitude of electric field keeps on decreasing. See, as it comes closer, magnitude increases. You can make out clearly. You see, very big magnetic field, electric field as it comes closer to the negative charge. How about if it is positive charge? Let us see. Keeping the negative charge back, now positive charge. You can make out this one. See, the direction of the electric field is away. right. As I bring it closer and closer, the magnitude of electric field keeps on increasing, you know, it's a big electric field as it is coming closer to the charge, but the direction also you should be aware of, it's always away from positive charge. Okay, but it was towards negative charge, clear. So, I am keeping this electric field sensor back to it. Now, what about if it is a dipole, you know, positive charge and negative charge together, it is an electric dipole. Let us see how the electric field would be. You can see here the electric field directions. Okay, so, the electric field, where is the electric field acting is, you can make out clearly how the electric field is. Okay, so, the direction of the electric field will be in such a way that you can make out one thing, this is actually the perpendicular bisector. This will show that it is all you know, parallel. See, this line is usually what you call as the perpendicular bisector of the dipole. You can make out from this line, this is the perpendicular bisector of the dipole, right. I am keeping the just at the same time I will show you the direction of the electric field as well. See, what can you say, can you guess what will be the direction of the electric field if I am keeping it over here? How much is the electric field? Very strong electric field, you see, it will be added up, correct, as it is towards the, you know, in the perpendicular bisector. If you move ahead, you can again make out that it is again parallel to the axis of the dipole, correct. In fact, you should say it is anti-parallel to the dipole moment, because dipole moment is from negative to positive. So, you can make out clearly, see, this is electric field in this direction. So, as it is towards the center, the value keeps increasing, right. So, this is the case of dipole, okay, equal opposite charges. So, I am keeping this electric field back to it. That's how we understand the concept of the electric field, and you can clearly make out what's the direction of the electric field from this diagram. And you know, if many charges are there, what you say, you might have studied about the superposition principle. You can even make out, if suppose I have so many positive charges, so how will the direction of the electric field lines be? See, you can make out, show electric field, you see the pattern. So, the different directions, you can clearly make out how the electric field lines are away from a positive charge, okay, and the direction is like this. Is that clear? And again, the electric field line, you know, you see it is closer towards the because these three charges dominate, so that is the reason why the direction is towards it. So, this is the way the electric field directions are at different points, you can make out. Okay, so, this is when there are multiple charges. If I keep a negative charge also close to it, see the value of electric field decreases, you can make out, because the electric field is you know, opposed by the field due to negative charge. Okay. So, that is one thing. So, now hope you understood the concept of electric field. By the way, what does the electric field mean? What do you mean by electric field? Electric field means electric field strength. Whenever you keep 1 coulomb, otherwise unit positive charge at a point, how much force that unit positive charge experiences, that is nothing but the strength of the electric field at that point, okay, you know that. So, that is about electric field, and before moving on to that, I will show you another simulation that will help you to understand what is the case of capacitor. Look at the screen. See, a capacitor, you can see it is, if I increase the voltage of a capacitor, what is happening, you can make out it is being charged. See, I am supplying a positive charge on the upper plate and negative on the lower plate. So, you can clearly make out that it is charged, the plates are charged, you can understand this point. You know, when I am disconnecting a battery, see, fully over, charges remain there. You got it, this is a charged capacitor, before it was uncharged capacitor. Okay, you see what happens when a dielectric slab is, this is a dielectric slab, what happens when dielectric slab is inserted, what happens to the value of capacitance? See, I will show you the capacitance value as well. See, when dielectric slab is not there, see the value of capacitance is this much. If I am keeping a dielectric slab over here, then the capacitance increases, you can see the value. When dielectric slab is inserted between the plates of capacitor, the capacitance increases. Okay. And to the plate charges, you can also show the plate charges. Here, since there are no charged plates, no charge over here. So, if I increase the voltage, if I am supplying a voltage, you can make out when voltage is supplied, when battery is connected, it becomes charged. So, it will possess some energy as well. This the third diagram, this represents the energy possessed by the capacitor when it is supplied a given voltage. right, and also you can connect the, you can measure the potential difference. You can see the potential difference between the plates like this, you can measure. See in the, on the voltmeter you can make out it is around 0.24 volt that is available from this, right. But one more aspect is, if I am keeping multiple capacitors, you can make out one thing. See, just two capacitors when connected in series, what you can make out? First capacitor, two capacitors are there. How are they connected? This way of connection is what is called series connection. Now it is not supplied any voltage, now I am giving a potential difference. So you can make out this is positive plate, you know, the top plates are positive, the bottom one is negative plate. Alright, so let us see what will be the potential difference. Will it be the same? You can make out, see, this is one second terminal. So I see that negative 0.42 volt, 0.42 volt is what is there. Similarly, what about this one? That also you can see it is 0.42 volt only, that is because they have same capacitance. How about if this capacitance increases? See the value of capacitance, by changing the plate separation I am increasing the value of capacitance. When capacitance increases, what happens is PD across this becomes, you see, when capacitance increases in series combination 1, PD across the second capacitor increases, whereas you see PD across the first capacitor will become less. See, now we measure the potential difference between the two capacitors, this one as well as the other one. Okay, so this PD increases, the other PD decreases when you increase the capacitance. First let us see, now let us see what about the charge possessed by them. So we can clearly make out, see, show charge, stored charge. If you find the charge on this is this much, in both the charge would be the same only. There is no variation in the amount of charge because they are in series. And second case is they are in parallel. See, this is a parallel combination. Stored charge is like this, you know, okay, because this much potential difference applied, we are providing the PD, accordingly charge is also stored. And what you can make out about the PD, potential difference across this, whatever be the value of capacitance, this PD is, see, you can make out 0.445 volt, and the other PD is also, you can see the same PD itself is there, 0.45 volt, there is no difference. Why? Because they are in parallel. How about this PD, if I am changing the what is the value of capacitance of one of the capacitors, you see, just I am increasing one capacitance, what happens to the PD? See, this is 0.446, no, before it was 0.46 only, now you see same 0.46 only. So both the capacitors, even if capacitance have different values, potential difference being parallel, potential difference is the same. Is that clear? That is the situation about series and parallel combination of the capacitor. So total capacitance value you can make out, total capacitance will be the sum of the two, correct. Whereas in if they were in series, see, they were in series, total capacitance will decrease. See, only one capacitor, if I show a single capacitor, you can make out 0.1 into 10 to the power minus 12 farad, right. If there are two capacitors in series, the value is still decreasing, three capacitors in series, further it is decreasing. Is it clear? This is how we understand the concept of series and parallel combination of capacitors. So let me come to some important points, that is, what if the capacitors are connected in parallel? If the capacitors are in parallel, which quantity will remain the same? Potential difference, correct, and charge will be stored in the capacitors according to their capacitances. Whereas in series combination, what would be the same in all the capacitors? Each capacitor will have the same amount of charge, but what would be different? Potential difference will be different. This is the major aspect you should understand as far as the capacitance is concerned. Is that point clear? Okay. So now, based on this, we will now, I think it is a time for us to move on to the some of the questions which I will show you from board papers. We will discuss some questions. When we do these questions, be very clear. If you did not get the concept clearly, you can call us and ask, okay. And also you note down the question and how it is worked out. We'll you know, you have to learn it thoroughly now itself. Further, what you should do is, the next step is you keep doing these similar questions later on more and more. That will help you to understand more about these questions. Okay, these all questions are randomly picked up from some of the board papers. Is that clear? Now have a look at the question. Two identical parallel plate capacitors C1 and C2 have capacitances C each. the space between this plate, there is a correction, the space between the plates is now filled with dielectrics as shown. If the two capacitors still have the equal capacitance, obtain the relation between the dielectric constants K, K1 and K2. Let us work it out. Obtain the relation between K, K1 and K2, right. Okay, now listen to this. I hope you can see the board. See, a single capacitor has a capacitance, let us write it as, it is given as C, that you may write it as epsilon 0 A by D is the capacitance initially. When you fill it with dielectric, the first case, how the capacitance filled with dielectric is like this, right. This is with capacitance, dielectric of dielectric constant K. So, what will the capacitance of this become? That will be K times the original capacitance, that is C1 you can write as Kc. Is that clear? Let this be one equation, K times the original capacitance. Now, the next thing is you fill the dielectric in a different way, that is half with one dielectric constant, with dielectric constant K1, alright, the other half with dielectric constant K2. So, K1, K2, alright. So, now what will be the new capacitance? We can consider this as two separate capacitors. Okay, this will be, we can draw one capacitor like this, second in this way. So, they are considered to be connected because the plates are connected together now. So, they are considered to be connected in parallel. So, in a parallel combination, what would be the effective capacitance? Just add the two values, correct? Addition of the two capacitances. How do you add the two capacitances? Like, first of all, how much is this capacitance? You can say K1 into, what is being divided here is compared to this one, the area, correct. So, we may say K1 into A or epsilon 0 A by 2 by D is this capacitance. How about the other one? Otherwise, we can rewrite this as K1 into C by 2, correct, because epsilon 0 A by D is C, alright. Similarly, this you can write as K2 into C by 2. So, the two capacitors, this is K1 into C by 2, this is K2 into C by 2, alright. Now, what you do is, since they are in parallel, we can add them up. When you add them up, you get a capacitance of C2 given. C2 is K1 C by 2 plus K2 C by 2. So, C by 2 into K1 plus K2. This is the capacitance in this setup. Now, what else is given? The two capacitance still have the same capacitance. They have the same capacitance again. It means what? You just equate these two. C1 is equal to C2. So, it would be what? Kc is equal to C by 2 into K1 plus K2, right. So, C cancel. So, what you get? K is equal to K1 plus K2 by 2. If you understood the question. So, once again look at the question. Two identical parallel plates capacitors C1 and C2 have capacitance C each initially. The space between their plates is now filled with dielectrics as shown. If the two capacitors still have equal capacitance, obtain the relation between dielectric constants K, K1 and K2. Now, again look at the board, the value of first capacitance, originally this much capacitance filled with dielectric of dielectric constant K. So, this becomes Kc, this is the first one. Now, it is connected like this or filled in this way. So, it can be considered as two capacitors connected in parallel. So, these two you can say first one and second one, correct. Then being parallel, we just add them up. So, we get C2. Now, it is given in the question they have still the same capacitance. So, C1 you can equate with C2. So, finally, we get this equation which is the question. I hope it is clear, right. So, now you move on to the next question. Just look at the next question. By the time you go through the question, I will rub it off and you will be ready for the next one. Okay. I hope you understood this question. Some of you might have done this question before, that is amount of work required to rotate a dipole from its position of dipole moment is given from its position of stable equilibrium to a position of unstable equilibrium in a uniform electric field of intensity 10 raised to 4 Newton per coulomb. Okay. So, what all quantities given over here is dipole moment. Now, you can see the board 3 into 10 to the power minus 8 coulomb meter is the dipole moment and stable to unstable equilibrium to rotate, how much work is done, that is the question. Electric field intensity is given as 10 to the power 4 Newton per coulomb. So, what is the question? how much work is required to rotate it from stable equilibrium to unstable equilibrium. So, first let us see the meaning of stable unstable equilibrium. Stable equilibrium means you can say it is like minimum potential energy. Minimum potential energy is when theta is 0, and maximum potential energy when it comes when theta is 180. 180 means theta is the angle between dipole moment and electric field intensity. Okay, it is 180 degree. So, we are going to consider we have to calculate the work done to rotate it from 0 degree to 180 degree. That is the meaning of saying stable equilibrium to unstable equilibrium. Alright, so what is the equation we have for the work done to rotate the dipole? P E into cos theta 1 minus cos theta 2. Is that clear? So, that way W is equal to P E into cos theta is 0 minus cos 180 degree. Okay, so cos 0 is 1, 1 minus minus 1. So, 2, this is minus 1. So, 2, so the answer is 2 P E. Okay, that means 2 times dipole moment is 3 to 10 raised to minus 8 and E is 10 raised to 4. That many joules is the work done. So, just substitute only now. Okay, 3 into 10 to the power minus 8 into E is 10 to the power 4. So, your answer is then 6 into 10 to the power minus 4 joules. This is the amount of work done to rotate the dipole from stable equilibrium to unstable equilibrium. It is a very typical question, it is a simple question, but right. Now, you see the next question. See the next question. Have a look at the question first. Go through the question, all of you go through the question carefully. A test charge q is moved without acceleration from A to C along the path A to B and then B to C, right, in the electric field as shown. E. Calculate the potential difference between A and C. Which of the two is electric potential more and why? Okay, all of you look at the questions, look at the diagram. I will show it on the diagram itself. You see, this is the diagram. You can make out one thing. Question is to calculate the potential difference between A and C. You see, potential difference between these two. What is the equation for calculating potential difference in terms of electric field? We have an equation V is equal to E dot dl, or we can also write it is E dl cos theta. E is the electric field, it is given as E. dl is the length of the line. Length of the line from the diagram you can make out 6 minus 2. So, 4, 4 meter is the length of the line. 4 and cos theta you can take as cos 0 because along the same line cos 0 is 1. So, the answer to this is 4 E is the potential difference. Now, again look at the diagram. The question is at which point of the two is the electric potential more and why? Can you make out? At which point is the electric potential more? Meaning where the potential is high potential. So, can you say what is the direction of the electric field from where to where? Okay, electric field is from positive to negative. You can see on the diagram from positive to negative the electric field lines are coming like this. So, the point C is here, A is here, B is here. Okay. So, which point the potential is more, which of the 2 points potential is more? So, potential will always be more towards which point? Out of A and C. What is asked is out of A and C, in which point potential is high. Sorry. Always potential is high where or near positive side. So, positive comes here because electric field is from positive to negative now. So, the arrow is like this, it means it is from positive to negative. So, the electric field is always high at the point near the positive charge. So, we should say or positive side. So, we should say the answer is C. So, potential is high at C. Is that clear? So, the answer to both the questions, first question the answer is potential difference between A and C is 4A, and which point is at a higher potential of A or C? We said it is C because it is closer to positive charge, And one more point to understand at this point, let me tell you one more question, one more question is asked based on this, that is the direction of electric field along the rise or fall of potential? That was the question. Once again I will tell you the question. is the direction of electric field along the rise or fall of electric field, sorry, rise or fall of the potential, in which direction the line is. You know, the electric field line is always on positive to negative. Also, you know, positive side high potential, negative side low potential. So it further means fall always means high to low, high potential to low potential is a fall. So what does it mean? Positive to negative, high potential to low potential, positive to negative. So electric field is always along the fall of potential, not to the rise. Is it clear? With that note, we will continue with some more questions. We will go for a short break. After the break, we will come back and we will discuss more questions. So you have to stay tuned, and we will have a short break now.